Hey everyone, welcome back to physics. This will be lecture 11 of the course. And in this section, we're going to go through a series of problems and examples from the larger, broader unit of Unit 2, motion in 2 or 3 dimensions. So we'll kind of wrap up this motion in 2 or 3 dimensions, a broad section with some nice examples and some practice problems. So let's go ahead and jump into it. And again, we'll call this section 2.5, problems and examples. I've got 4 problems that I want to work through in this video. 2 of them are just kind of 2 and 3 dimensional, well, 2-dimensional kinematics type problems. One of them is a circular motion problem, and then one is relative velocity problem. So let's go ahead and start with the 2D kinematics. And so my first example, I'll call example number 1, and I'm just going to refer to it as the how high problem. Okay, so it'll pertain to identifying the starting height of a projectile. So let me go ahead and read through the problem first, and then we'll write it down, and then you should pause the video, work on it yourself, and then I'll go through the solution. So here's the setup. A rock is thrown with speed 12 meters per second and a launch angle of 30 degrees from an unknown height. The rock travels a horizontal distance of 19.5 meters before hitting the ground. The question is, from what height was the rock thrown? Okay, so a rock is thrown with speed 12 meters per second and launch angle theta equals 30 degrees from an unknown height. Okay. The rock travels a horizontal distance of 19.5 meters before hitting the ground. Okay. And the question is, from what height was the rock thrown? Okay. All right, so just to kind of draw the picture here. So you've got a rock, you got some kind of a cliff here, right? And you're tossing this rock off of this cliff at an angle of 30 degrees with an initial velocity of 12 meters per second. Now the thing's going to fly through the air and it's going to land somewhere out here, right? And that somewhere happens to be 19 meters from where it was thrown. Okay, so then the question is, how high, given the fact that it's tossed at this velocity and it goes this distance, how high was it thrown from? So this cliff, how tall was it? All right, so that's a basic setup. And usually if you're given some kind of a projectile problem like this, at least with me, I usually just want to, right off the start, I want to break that initial velocity into its x and y components. That's what I like to do. So I like to just start with that, right? And so basically you've got a triangle here. You can think of this as a triangle. Now after you do a few of these, you don't have to write it down every time, but you should just be able to remember how this works. But you got a triangle like this. This is your x. This represents your x velocity. This represents your y velocity. And of course 12 is the given velocity. But the sine of 30 degrees is equal to adjacent over hypotenuse, so that's your y over 12, and then the cosine of 30 degrees is x over 12, right? And so from that you can calculate that y would be equal to 12 sine of 30 degrees, which when you run that through a calculator, you'll see that that's going to be 6 meters per second. And then your x velocity is going to be 12 cosine of 30 degrees, which turns out to be about 10.4 meters per second. Okay, and so That's just handy to have. It's really super quick to find them, and just take that 12 meters per second, figure out what the I and J components of it must be. All right, and so remember, we're trying to figure out how high the ball was thrown from. We don't have enough information to just directly calculate this. So what we need to do next is we need to figure out the flight time. How long was the rock in the air? Now we know the distance it traveled. We know the velocity in the x direction, and given those two things, we can figure out how long it must have been in the air, right? So the next step is to determine how long the rock was in the air. Okay, and that's just a simple x final equals x initial plus the initial velocity in the x direction times delta t, right? And we have all of this information, so 19 meters is the final position, 0 meters was the initial position, plus that x component of velocity, 10.4, times delta t, and we can of course solve for delta t here, and we'll see that the time in the air must be equal to 19 meters over 10.4 meters per second, which when you do that calculation, you'll see that that's about 1.88 seconds. Okay, so the rock gets flung off of this cliff and it's in the air for 1.88 seconds. Now, given the fact that we know how long it was in the air, we can now figure out how high the cliff must be, right? So we can use the y component of position, or we can use the y position function to identify the initial height, right? So what we're going to do is we're going to use this guy, y final equals y initial plus the initial velocity in the y direction times t plus 1/2 a t squared. So the final position on the y-axis would be 0 meters. The initial position in the y direction, that's what we're after. That's our h. Okay, what's its initial velocity? Well, that's the y component of the velocity, and that's 6 meters per second. And we know the time it was in the air is now 1.88 seconds. All right, and then we just plug in the acceleration piece here for gravity. So we get plus 1/2 and then minus 9.8 meters per second squared times 1.88 seconds squared. So just plugging in all the information, we can easily then solve for h. And when we do that, what do we see? We see 6.04 meters approximately. Okay, so the initial height of the rock must have been approximately 6.04 meters above the height of wherever it landed, right? So looking back at this picture, this must be 6.04 meters, right? And then you can test this by just kind of calculating some various things using this as an initial y position. You can just use some different formulas to check this if you like. Right, but that's a nice simple kinematics problem, 2D kinematics problem that that isn't just a straight plug and chug. You'd have to think a little bit about like, okay, what information do I have and how can I use that to get to the information that I want. Okay. Perfect. That's example 1. Let's take a look at the next example. This is a little bit trickier example, and I'm going to call this one the skateboarder example. The skateboarder. Okay. So I'll read the problem again first, and then we'll write it out and kind of piece together a picture of what's happening here. So the problem goes, a skateboarder starts up a 1 meter high ramp at a speed of 6.1 meters per second. Assume no friction and assume that the ramp has an angle of 30 degrees. Now at the top of the ramp, the skateboarder leaves the ramp and sails through the air. The question is, how far from the base of the ramp will the skateboarder land? Okay. All right, so let's write this out. A skateboarder starts up a ramp, starts up a 1.0 meter high ramp at a speed of 6.1 meters per second. Now we assume no friction, right? Let's simplify the problem. Assume no friction and a ramp angle of 30 degrees. Now at the top of the ramp, he sails through the air. So he sails through the air. Question is, how far from the base of the ramp will he land? All right, so you're given very little information here. You really just know the speed of the skateboarder as he hits the ramp. The question is, how far is he going to go? All right. So the basic setup is this. This may seem straightforward on the surface, but when you really think about it, it is a little bit more challenging. So I've got some kind of a ramp here, and I'm told that it's got a 30-degree inclination here. It's a 30-degree ramp. I'm also told that it's 1 meter high. Okay, so it's 1 meter off the ground at the top. Now, here's the part that makes it tricky. Here's what kind of makes this a trickier problem. We're not told the velocity of the skateboarder as he leaves the ramp. We're told the velocity of the skateboarder as he enters the ramp. So down here, we're told that his velocity is 6.1 meters per second. And now we know he's going to fly off of this thing and he's going to touch down somewhere. And what we're asked to figure out is, what is that distance? What is the distance to the landing, right? So let's consider this the base of the ramp. So how far out here does he land? And so to really answer this question, we have to know how fast the guy's going when he leaves the ramp, right? That's going to matter, right? So we really need this thing here first. We need what I'm going to call V1, velocity at the top of the ramp. Because you can imagine what's going to happen. He's got a certain velocity as he goes into the ramp, but he's going uphill there, right, for some distance, and gravity is going to slow him down, and his actual speed as he goes into free fall is going to not be 6.1 meters per second. It's going to be something smaller. Okay, so we're going to do this problem in a couple of steps. The first step is that we're going to need to calculate the skater's velocity when he exits the ramp. Right. In particular, we need to identify the change in his velocity as he goes up the ramp. Okay, so let's think about this ramp first. There's information that we need to get in addition to what we have here. So we need to know this distance in particular. Like, how long is he on the ramp? What is that distance up the ramp? So first of all, how long is the ramp? Right, and so this is just simple trig calculation, right? We know that it's 30 degrees here. We're told that one of the legs is 1.0 meters, and this is be the hypotenuse here. We just need to know that hypotenuse, don't we? And so we know that the sine of 30 degrees is equal to the opposite side over the hypotenuse, so it'll be equal to 1 meter over h. And so that means the hypotenuse would be 1 meter over the sine of 30 degrees. And so when you do that calculation, you'll find that the length of the ramp is 2 meters. So h is equal to 2 meters. Okay, well that helps. So now we know that this is a 2 meter long ramp. Right, and so we're going to use that information specifically to figure out, because basically we need to know the acceleration while he's on the ramp, namely he's going to slow down. Gravity's going to act on him, and it's going to act on him over a distance of 2 meters. So that's helpful. We need that. Okay. All right, so the skateboarder hits the ramp, starts to slow down. How rapid is the slowdown? Now that's going to be a function of gravity. It's also going to be a function of how steep the ramp is here. It's a 30-degree incline. It's also going to be a function of, not well, his overall velocity change will be a function of the distance, but we want to know what's the acceleration while he's on the ramp. Okay, so the skater is slowed. He's slowed due to gravity as he moves up the ramp. Okay, so let's think about how this is going to work, right? So let me draw the ramp here. All right, and so I'll just put a circle on here just to represent the skateboard. It doesn't matter the shape, just an object is on the ramp, right? Now, the velocity is in that direction. That's our v. The acceleration that's going to counteract the velocity is going to be in the reverse direction, right? There's more acceleration. Now, really, the acceleration is based on gravity, which is going to be pulling straight down here, right? So the acceleration is not going to be minus 9.8 meters per second squared. It's going to be some scaled version of that that's based on the inclination of the ramp. And so if you think about a triangle that you would draw in here, right, where maybe this is a right angle, this is the, negative 9.8, right? This is the side we need to know. We need to know this side, right? That's going to be the part of gravity that's contributing to this skater's slowdown. Okay, and so if this is 30 degrees, then this must be 60 since that's 90. Okay, and so we know that the cosine of 60 degrees is equal to the adjacent side, which is what we're after here, over the hypotenuse, so negative 9.8. So that means the acceleration here that the skater that works on the skater is going to be equal to negative 9.8 meters per second squared times the cosine of 60 degrees. Okay, and when you crunch all of that, then you'll see that A is equal to negative 4.9 meters per second squared. So about half the magnitude of gravity in free fall, right? Because there's an inclination here. There's this ramp, right? So the acceleration the skater experiences as he moves up the ramp is negative 4.9 meters per second squared. And so the skater's velocity starts out at 6.1 meters per second, and it's slowed by this acceleration over a distance of 2 meters, right? And so we can figure out that final velocity by using this equation, Vf squared, so the final velocity squared, remember, is equal to the initial velocity squared plus 2 times whatever the acceleration is over the distance that acceleration is being applied. And so we know initial and A, and we know delta x. And so this would be equal to 6.1 meters per second squared plus 2 times the acceleration that we just calculated minus 4.9 meters per second squared times delta x, which we figured out earlier is 2 meters times 2 meters. Okay, and so that all works out to be, when you crunch all of this, you get 17.61 meters squared per second squared, right? And so then if we take the square root of that, we see 4.2 meters per second is the positive quantity. All right, so what that's telling us is that the final velocity at the top of the ramp, after we traverse the 2 meters to get to the top of the ramp, our speed has slowed from 6.1 meters per second down to 4.2 meters per second. Okay, very good. So let's redraw this. Let's redraw our picture here. Now we're on phase 2 of the problem. All right, so now we've got this ramp. 30 degrees is still important, but now we know that the velocity, the initial velocity, is 4.2 meters per second. Okay, and the guy's going to leave that, and he's going to get airborne, and he's going to crash down, and we still want to know what this distance is. All right, so all of that work was just to figure out how fast is the skateboarder going when he becomes airborne. And now we know 4.2 meters per second. We know the angle is still 30 degrees off the horizontal. And we know that it's 1 meter off the ground at the top. Okay. So given this information, now we can turn to the larger problem of determining the skater's distance in the air. Now, notice we can't simply use, so we can't simply use this guy. We may want to x final equals x initial plus v initial x times time plus 1/2 a t squared. We can't do this here in this case because we do not know the distance and we do not know the time, right? We're looking for distance and time is not given. So we have to figure out either distance or time in some other way, or else bring some other equation into, because we have two variables, two unknowns in one equation, right? So it's not going to work out. So what I propose we do instead is we think about the problem in stages. So we leave the ramp, we crash down. Now let's call the moment we leave the ramp, we'll call that T0. And then the moment we crash down, let's call that T2. But in between, there's another time that's important that we can use, and that we'll call time 1. And that's the time that the skater is at the height of the trajectory. And I'll denote that with H. Right? We don't know the time from T0 to T2, right? And we have no hopes of finding it with just this equation. But we can figure out how long it takes for the skater to leap before he gets to the highest point in his trajectory. We can figure that part out. And the way we want to do that is we can use this equation. V final in the y direction is equal to V initial in the y direction plus a y, in this case acceleration, times time. Okay, so your final velocity is equal to your initial velocity plus acceleration times time, right? And the reason that this is going to work is because we know the final velocity, 0 meters per second, right? Namely up here, right? When you get to the top, your velocity in the y direction is 0, and you start to turn around and come the other direction, don't you? So 0 meters per second is equal to the initial velocity in the y direction, which if you turn back a page, you'll note that is 4.2 meters per second times, but you have to take just the y component, so just times sine of 30 degrees. Plus, now what's the acceleration? Well, in the y direction, the acceleration is due to gravity, right? This is projectile motion, right? And so it's negative 9.8 meters per second squared. And then t is the quantity we want to find, right? And this is going to be our T1 in particular. I might just use that T1 here. Okay, and so basically I'm saying 0 is equal to 4.2 times the sine of 30 degrees minus 9.8 T1. And so if you solve that equation for T1, you'll see that the time from the top of the ramp to the top of the trajectory is equal to 0.2141 seconds. Okay, so it takes 0.2141 seconds to get there. Now, if we can figure out how long it takes to fall from there, we will have the total time, right? And then we can come back up here and just use this guy. So next, how long does it take to fall from the highest point? Well, how long does it take to fall from this point up here? Well, first we need to know how high we are, right? If we can figure out how high that point is, then we can definitely figure out how long it takes to fall from it. So we could say y final equals y initial plus v naught y times t plus 1/2 gt squared. This will get us how high this is, the final position of the final y position. Okay, and that's just going to be a plug and chug, isn't it? So we put in 1 meters, right? We start at the top of the ramp, 1.0 meters up. We start here and we go up to this height. Start here and we go up to this height. So 1 meters, YF is what we're looking for, 1 meter plus, what's our initial velocity? Our initial velocity in the Y direction is 4.2 meters per second times the sine of 30 degrees. How long are we in this? What's the initial velocity? What's the time here? Well, we just found that is 0.2141 seconds. Okay, and then plus, we got to add in the gravity component. It's going to slow us down. So plus 1/2 times negative 9.8 meters per second squared, and then times 0.2141 seconds squared. So everything is known. 1 plus 4.2 sine 30 times 0.2141 plus 1/2 negative 9.8 times 0.2141 squared. And we can just run all that through and we'll get, everything will end up in meters. And so what we'll find out is that this is equal to 1.22 meters. Okay. All right, so we know that it takes us, we leave the ramp at a certain velocity, a certain inclination, and 2.2141 seconds later, we are at the top of our trajectory, which happens to be 1.22 meters. Okay, so we go up that high. Now the question is how long does it take us to fall all the way down, because that'll tell us this time. Okay, so how long does it take? Well, that's again just another iteration using this same expression, right? So here what we'd want to say is, well, yeah, so how long would it take us to fall, right? So we would say y final, what we would use is this equation again, y final equals y initial plus initial velocity in the y direction times time plus 1/2 gt squared. All right, this time we know the final position is 0 meters. And we know the initial position is 1.22 meters. Right, we start at the top, we fall to the bottom. And our initial velocity, when we're at the top, we're going 0 meters per second. And we do that for t seconds, which we don't know yet. And then minus 9.8 over 2 t squared. Okay, just kind of plugging all that in there. Right, and so what we end up with here is a quadratic equation. And so what we get is 0 equals 1.22 minus 4.9 t squared. All right, but this one is super easy to solve, and you subtract 1.22 from both sides, divide by 4.9, and what you'll see is that t is equal to plus or minus the square root of 0.2499 approximately. And so, of course, you'll get a positive and a negative answer. The positive answer is what we're interested in here, and that is 0.4999 seconds. Okay, so it takes us about 1/2 second to fall from that height. Okay, and so what does that tell us? Well, that tells us that this piece here is 0.4999. Okay, so what's the total time then? Well, the total time that you're in the air must be equal to how long it takes you to get to the top, and then how long it takes you to fall all the way from the top. And so the total time is equal to the sum of these two. So 0.2141 seconds plus 0.4999 seconds. Okay, and when you add all of that up, you see it's 0.7140 seconds. Okay. Now remember, what we're trying to get to is we just want to know this distance. Well, now I know, I was given the horizontal velocity, I was given the initial velocity, I can figure out what that is for the horizontal direction, right? And I know where I start, I know, 0 here. I just need to plug the amount of time that I'm airborne into my horizontal position function, right? So that's what we're going to do. That'll be the last step. And so we can say x final equals x initial plus the initial velocity in the x direction times the time. Okay, and so x initial is 0 meters. I start at the base of the ramp, which I've coordinatized as 0. And my velocity, initial velocity in the x direction is 4.2 meters per second, cosine of 30 degrees. And now I know the time, 0.714 seconds. And I can plug all that in, and I see that I get 2.9 meters. All right, so the skateboarder is going to land approximately 2.9 meters from the base of the ramp. Okay. All right, so we see that the skater goes up 1.22 meters. So it doesn't go terribly high off the top of the ramp. The ramp itself is 1 meter. 1.22 meters high, and about 3 meters from the base is where the skater will land. Okay. So kind of an involved kinematics problem. I mean, you're given very little information to start with. You know how high the ramp is, and you know the speed at which you hit the ramp. That's about it. And from that, we can figure out everything that we need to about the trajectory of this skateboarder. All right. Excellent. Okay, good. So we did that one. The next problem, example 3, is going to be a problem involving relative velocities. So we'll call this example number 3. And this one I'm going to call airplane heading. Okay. And so again, I'll read the problem out, and I think this one's very familiar if you watched the lecture, a couple of lectures back on relative velocity. It's very similar. It's a different scenario, and it's a little bit different, but it's very similar to the boat crossing the water problem. All right, so here I'll read out the problem first. An airplane is headed due north. Its airspeed shows that it is moving through the air at 240 kilometers per hour. If there is a wind of 100 kilometers per hour from west to east, what is the plane's velocity relative to the Earth? Okay, so that's the main question to start with. And then secondarily, if the pilot wants to correct for the crosswind, what angle should he make with due north? Okay, so let's write this down and we'll draw a picture. So an airplane is headed due north. Okay, its airspeed shows that it is moving through the air, key word there, through the air, at 240 kilometers per hour. Okay. Now, if there's a wind, of 100 kilometers per hour from west to east, what is the plane's velocity relative to the Earth? What is the plane's velocity relative to the Earth? Not relative to the air, relative to the Earth. Okay, and that's the first question. And the second question is, if the pilot wants to correct for the crosswind, what angle should he make with due north? Okay, so this is a navigation problem, right? So let's draw a picture here. And I'm just going to use a circle to represent the airplane, right? So this is the plane. Now the airplane is, and we'll say north is up. Okay, the plane is moving north at 240 kilometers per hour. Now that's its speed relative to the air. Okay. And then, so the plane is moving north, so this is the north direction. From there's a wind blowing from west to east, which means something like this, and that's going to be 100 kilometers per hour, right? And so similar to the boat in the water problem, right? The air is going to push the airplane, right? The air is going to push the airplane off due north, right? It's going to kind of, even though it thinks it's heading north through the wind, which it is, it's getting pushed by the wind off course. Okay, so let's think about the frames here. We've got, we'll just call A, we'll let that be the air. And then the other one is the earth, right? In the river problem, you had the water and you had the shore, the land. And now we've got air and the earth. Okay, but what's our relative velocity equation? Well, in this case, it'll be the velocity of the plane relative to Earth. That's what we're interested in. That's going to be equal to, right, that's kind of this side here, isn't it? It's going to be equal to the velocity of the plane relative to air plus the velocity of the air relative to the Earth. Okay. And we can kind of think of, let's put some coordinates on here. Let's say that this is the y direction and this we'll call x, so this will be I and j, right? And so we can plug these quantities. The velocity of the plane relative to the air is given as 240 kilometers per hour, and that's going to be the j direction, isn't it? And the velocity of the air relative to the earth is given as 100 kilometers per hour, and that's the I direction. Right, and so this can be, you can kind of say then that the velocity of the plane relative to the Earth is 100 I hat plus 240 j hat kilometers per hour. Like that's the velocity vector, right? What's the speed? Well, it's just the magnitude of that. So let's figure that out quick, just so we know. The speed of the plane is going to be the magnitude of the velocity vector. And so that's going to be equal to 100 squared plus 240 squared. And you take the square root of that. And you get 260 kilometers per hour. Right? So the plane is going to be moving along this path slightly faster at 260, right? And what is that angle? What is that angle off north, right? So if this is due north, what is this angle? The angle, if you think about this as just a triangle with, these three sides, it'd be 240 and 100. So this angle, so this is the north direction. Pardon me. That's the north direction. Then we can use just the tangent. The tangent of theta is equal to the opposite over the adjacent, so 100 over 240. And so theta is the inverse tangent of that ratio. And if you plug all that in, you should see about 23 degrees. So the wind is pushing the plane 23 degrees east of north. So the wind is pushing the plane 23 degrees east of north. All right. So that's part one. I mean, so this is all the velocity vector information you need. You've got the actual velocity vector. Now you know the airspeed of the plane relative to the Earth, and then you even know the degrees. So we kind of gave a little more information there than was strictly needed. So now the question is, if the pilot wants to correct for the crosswind, what angle should the pilot direct the airplane? And I'll give you a hint. It's not 23 degrees west of north, right? There's more to consider than just that. You don't just angle it another 23 degrees off, right? So what we really need to do is we really need to adjust this velocity vector and make it into a function of theta. So given that we have the velocity of the plane relative to the Earth being equal to the velocity of the plane relative to the air plus the velocity of the air relative to the Earth, this piece here needs to be adjusted. right? That's the part that the pilot actually controls. The pilot can control the plane's velocity in the air. He can't control the air and the velocity of the air relative to the Earth. And through this course correction here, he can adjust this. So this is the piece that we're after, right? And so let me flip the page and then we'll draw a little picture of what's happening here and how we have to think about this. Okay, so again, I'll draw the plane, and here's the north line. This is the line that we would like the plane to stick to, right? But we've got this pesky crosswind coming through here, right? So this is the crosswind. Now, in order to counteract the crosswind, we have to angle the plane into the wind. And that angle is what we're after. How steep does that angle have to be such that we cancel out the crosswind? Okay. So the way to think about it is just use a triangle, and we need to break this velocity. So we're going to fly at 240 kilometers per hour, right, into the wind, and there's going to be some angle theta. And so what are the x and y components of that speed then? Well, again, just kind of breaking into some of our trig, we know that sine of theta is equal to the opposite over 240, and cos theta is equal to the adjacent side over 240. Okay, and so that's going to imply that the opposite side here is going to be 240 times the sine of theta, and the adjacent side is 240 times the cosine of theta. Okay, and so we can use these in place of our velocity of the plane relative to the air. So here, let's rewrite this. We've got the velocity of the plane relative to Earth equals the velocity of the plane relative to the air plus the velocity of the air relative to the Earth. Okay, and so what we're going to put in here is we're going to put these guys. Now remember, this is a negative value, right? This is the way we've coordinatized this. This has got to be negative. Okay, so that's this guy here. So this will be negative 240 times the sine of theta, and that's going to be in the I direction, plus this one, 240 cosine of theta, and that's going to be in the j direction. So just to make sure we're tracking here, this is all just this piece of the vector equation, right? So just that piece. And then we still have this guy on the end here, which was 100, and that's in the I direction, right? In the x direction, so I hat. Okay. And now what does it mean to correct for the crosswind? Well, what it means is that we're going to fly into the wind in such a way that we're not going to deviate from this north line, right? So the plane is going to be ever facing that direction, but it's going to stay in line with this north line. And so what that basically means is that the velocity in the I direction is going to be equal to 0, right? So we need the velocity in the I direction to be equal to 0. Okay, so 0. And so that's a simple thing. We've got two terms that relate to I, and so we say negative 240 sine of theta plus 100 needs to equal 0, and we can solve for theta. And so sine of theta should equal 100 over 240, and therefore theta is the inverse sine of that ratio. And so theta, when you plug all of that into a calculator, you'll find that theta is equal to 25 degrees. A little more than the angle that the crosswind is throwing the plane off of north. So just a little extra needed to keep it on path. Okay. All right, very good. So that means if the pilot steers 25 degrees into the wind, then the plane will head due north with no deviation from this line. Okay, perfect. All right, very good. One more problem, and this is going to relate to a circular motion type of problem. Okay, so example number 4. And I'm just going to call it tight corner. Not a long problem, but I think one that's reviews enough that we should be good. So I'll read the problem. A car has a maximum lateral acceleration of 0.87 g. This means that the max centripetal acceleration that the car can experience before it starts to skid is 0.87 g times 9.8 meters per second squared. Okay. Now, if the car is moving at 40 meters per second around a corner, what is the tightest corner that the car can go around? Meaning, what is the minimum radius of the corner such that the car does not skid? It sounds like a pretty hard problem, but it turns out it's fairly easy to answer. Let's write this all out. So a car has a maximum lateral acceleration of 0.87 g. And this means that the max centripetal force, the max centripetal acceleration, the max centripetal acceleration that the car can experience before it starts to skid is, and you can just multiply this out, 0.87 times 9.87 meters per second squared, and that is 8.5 meters per second squared. Okay, so it can experience a centripetal acceleration up to 8.5 meters per second squared, and then anything beyond that, the car is going to start skidding. Okay, it's going to start to slide. Now, if the car is moving at 40 meters per second around a corner, we'll say around a flat corner, meaning there's no banking on the corner because that's going to change things. If the car is moving at 40 meters per second around a flat corner, what is the minimum radius of the corner such that the car does not skid? Okay, a lot of words, a lot of sentences, a lot of questions. So if the car is moving around this corner, flat corner, and we know the velocity, the speed is 40 meters per second, and it's constant, right? So uniform circular motion. How tight can the corner be before the car starts to skid at this speed? Okay, and so just picturing the corner, right? I've got some kind of a corner here, and we could think of this as having a certain radius. The car's racing around the corner. Constant speed, it's not accelerating, not decelerating. Speed-wise, it's changing direction, of course, but it's the magnitude of its velocity is constant. So the question is, how small can this corner be? How small can R be? If R is really small, it's a super tight corner. If R is really large, then this might be easy, right? A school bus might be able to accomplish this with a large enough R. But this is presumably a race car because this is a pretty fast to be going around a corner, right? And so almost a full G of max centripetal acceleration is probably a lot higher than a school bus or any non-sports car vehicle could endure. So we can really, since it's uniform circular motion, let's just pull out the main equation here, and that is this acceleration. The radial acceleration is equal to the square of the velocity divided by the radius. And we can just rearrange this a little bit, and we'll see that the radius is equal to the square of the velocity divided by the radial acceleration. Now this radial acceleration, that is just the lateral acceleration, right? That is just the centripetal acceleration. So we can plug in our maximum centripetal acceleration, and that should tell us, that should translate into a minimum radius. Obviously, if I put a larger number in here, I'm going to get a smaller r. If I put a smaller radial acceleration, I'm going to get a larger r, right? Because it's velocity divided by this. Right, and so that means the minimum radius that the car can endure, given 40 meters per second as the velocity, and given a lateral acceleration that translates into a max centripetal acceleration of 8.5 meters per second squared, is about 190 meters. Okay. So this car going this speed around a corner with a radius of 190 meters is going to barely hang on, right? If the radius is 195 meters, it's going to be easier. If it's 200 meters, it's going to be really easy for this car. Now, if the radius goes below 190 meters, then that means the car is going to lose control going around this corner at this speed, right? That's the bottom line of this problem. Okay, so the tightest corner the car can handle will have a radius of about 190 meters at this speed. Of course, if you're going slower, then everything changes, right? If I'm only going 20 meters per second, then obviously the radius can be a lot smaller. Okay. All right, very good. That is the last problem that I have for this section. Next up, we'll move into the world of force, and so up to this point, we've been dealing with kinematics, and so we haven't really been concerned with forces. We've been mostly concerned with just motion and acceleration and such. But now we're going to take everything back another layer. We're going to peel back another layer and talk about forces and the interaction of forces and how forces are related to motion. All right, so that is it for now, and we will talk to you all next time. Take care.